Hello everyone, welcome to my presentation. I am MD Navid Binanwar. Today I would like to talk about time of use our priority-based multi-mode online charging scheme for EV charging station. To begin with, electric vehicles or EVs. EVs have been considered to be a key technology to cut down the massive greenhouse gas emissions from the transportation sector. To make the environment clean is really important. Currently in the market, there are three different kinds of electric vehicles available. One is called HEV or hybrid electric vehicles. One is PHEV, plug-in hybrid vehicle, or BEV or battery electric vehicles. In this work, we are particularly considering BEV, which is battery electric vehicles fully run on the battery. Next, let's see about charging mode. Currently, we have three different levels of charging mode available in the market. First, let's start with L1, which is level 1 charging. It takes 8 to 12 hours to charge a car, and the price is relatively low and is more suitable for the home users. However, for L2, is called level 2 charging. Is an AC charging mode. It takes 4 to 8 hours to charge an EVs, and it takes charging power 10 to 22 kilowatt, and it's a little bit expensive than L1, and it's also suitable for office and public locations. And then it's called L3 charging mode, or also known as DCFC. This is the fastest charging mode currently in the public charging station. It takes only 30 to 60 minutes to charge a car. However, it is more expensive and it's also charging. It also has a high charging power. It's between 50 to 120 kilowatt. That means it draws a lot of energy from the grid as well. And this type of charging station is also suitable for public charging station, especially for the people, those who are in rush. Next, let's talk about the state of charge or SOC. The battery state of charge or SOC refers to how much energy it left, whereas 0 means the battery has no energy left or no charge left, and however SOC 100% means the battery is fully charged. Next, we will talk about the time of use pricing scheme. We know electricity price is not constant over the time during a day. The electricity price goes up when the demand goes up. Also, it goes down when the demand goes down. It depends on how much energy is required at a particular time of a day. So TOU electricity price gives a real-time electricity pricing idea. So it will be helpful for the station owner to organize or to arrange and schedule their charging so that they could save money. The information that you can see in this here is from a French electricity transmission system operator, is RTE. Next, we talk about the demand response strategy, or DR. In that particular strategy, what is happening is that users voluntarily reduce their load during peak period by utilizing TOU. That means by utilizing TOU, we know how much, what is the electricity price at the current time period, and the users could reduce their energy consumption at a particular time of the day. And by doing this, they could get different financial and operational benefit from the electricity utility. Currently, three different kinds of demand response available. For example, the first one is curtailment. That means you just reduce the load from the peak period to the certain level. Second one is load shifting. So you change the load from different period of time when the demand is low. Or the valley filling is when the demand is low, you utilize the electricity more than other time. All these criteria has the basic meaning is to reduce the energy consumption when the demand is a peak period. Next, I'll talk about the challenges. EVs consume comparatively high power from the grid during the charging. Then it also needs frequent charging, and that results customer anxiety. And the another one is called charging duration. So all are the main challenges in EV scheduling. To mitigate the negative effect and enjoy the benefit of EV's integration, it is therefore critical to develop efficient charging control scheme. So motivation of this research is to and previously we have seen most of the previous work has been done based on single charging mode. However, there is no flexibility being considered because some people may choose L2, some people may choose L3. So it will be benefited if we could propose something with both charging modes. However, it's not being seen before. Also, another thing it can be seen from the existing work is that non-causal information of the EV charging, for example, the arrival time, departure time, and charging demand are well known prior to the arrivals of the EVs. To fill the research gap, the target of this research is to design a scheduling algorithm that will consider both available charging mode and serve the maximum number of EVs. Let's talk about the system model. There are three major parties involved when considering EV charging problem at a public charging station. From the figure you can see is called utility who produce the electricity and then another is called EVCS or electric vehicle charging station, and another part is EVs itself. So the utility produce the electricity and sell it to the EVCS, and EVCS sell this electricity to EVs. So in this work, we're particularly interested to 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 check the problem from the electric vehicle charging station point of view. Following this one, we have modeled the EV charging station, as you can see in the figure. So each charging spot is equipped with two different kind of charging station is charger L2 and L3, and they're connected through LAN, and there is CRS, which is charging regulator system, which this is responsible for scheduling all the EVs and is connected through internet to electricity utility. And that means the CRS could have all the updated electricity price during a day, hourly, and then it can scheduling the EV based on those information. Next, let's talk about the introduction to the proposed scheme. In this work, a priority-based online scheduling is presented to handle the online charging issue while taking dual charging mode into account. In addition to EV users, charging urgency, station capacity, and grid load balance. So we not only consider the dual charging mode, but also consider the user's urgency, station capacity, and grid load balance. So the proposed scheme PBOS has three major steps. Step 1 is feasibility test. Step 2 is charging priority ranking. Step 3 is optimized online scheduling. So look, let's start step by step. The first step is the feasibility test. In this step, what will happen when the charging station get a request from an EV, it will going to check whether it is possible to deliver the charge to that particular EV or not based on the information. You can see that equation 1 is developed based to measure these things. It has two parts. First one is define the initial SOC, and the second part measure the energy added within the dwelling time. So it means when an EV send the request, it will take the input, the initial SOC, and it will take input the dwelling time, and it will measure that how much energy it can be delivered to that particular time that the user selected. And the TD value, or the remaining charging time, can be measured by simply taking account the departure time minus the arrival time. Here Mn is another binary variables where it means the charging mode. 0 means L2 charging, and whereas the one means L3 charging mode. That is why we have two different equations based on this charging mode. Next, we talk about the feasibility test results. When the required SOC is higher than the expected, that means if the user asking something which cannot be delivered within the dwelling time, then it's not a feasible EV. So the request will be rejected. However, if it is not, then it is considered as a feasible. All the EVs those passes the feasibility test will go through the step 2. In this case, all the EVs will be ranked based on the equation 4. Again, we have two equations based on the charging mode. First one is based on charging mode L2 and second one is charging mode L3. What does this equation mean? The numerator part defines the required level of energy and the requested level of energy to fill the battery. And the denominator part defines how much energy it actually can be delivered to the battery. Or it can be seen in another way around. The numerator part defines that EV which has less SOC and require small energy, then it has more priority than the others. Now think about in a case when two EVs come with has same SOC requirements, however select two different charging mode. In that case, L2 always have the higher priority than L3. This is because the charging power of L2 is smaller than L3. But L3 user paid more money and it takes less time. This is why we have decided to give more priority to L3 users. And to make sure it could happen, we have introduced two different parameters, which is alpha and beta, known as the regulator parameters. Next, we utilize the time of use pricing by introducing ancillary parameter gamma I. In this equation, the Cmax defines the maximum electricity cost. Ci means electricity price at current time state, and C means minimum electricity cost. Step 3, we are introducing the optimizing online scheduling. The equation 7 in that you can see in the screen is the objective function where x and I, this is and binary variables. We need to know that the x and when the value of x is 0 means that EV is not being selected, whereas 1 means selected. Wn we have already discussed earlier is the priority weight, and gamma I is the value of electricity cost. And next we'll talk about the constraint. The first constraint defines the capacity limit of the station. Obviously we cannot have the full charging capacity all the time due to the peak load electricity price and considering the DR program. Second equation defines the charging spot capacity limits. Third one, maximum charging limit based on charging mode. As we know that L3 charging mode can be charged in L3 charging mode, an EV can be charged up to 80%. However, for L2, it can be charged up to 100%. So we need to make sure the EVs don't get overcharged in any way. The fourth one is the minimum charging limit of an EV. This defines when an EV get passed to the feasibility test and selected for charging, it must make sure that EVs get the required charge that it been requested before. And in the next part, we're going to discuss of the performance evolution. So to do this, we have considered these simulation scenarios that you can see in the screen. Here you can see in the y-axis the electricity price in the left side, and the right side is the EV charging station capacity. So the capacity of the charging station is not remain same as I have earlier mentioned due to the DR program. It goes down when the electricity price seems very high in the day. and the green bar chart that shows the EV arrivals during a day. This is from an historical dataset. Next, we talk about the simulation result, begin with the rejection rate. What does rejection rate means is in a particular time, how many EVs the scheme could serve, that how many EVs it cannot serve in a whole day. That is compared with the other schemes. So we have considered FCFS as a benchmark scheme and also RTCS as a benchmark scheme and compare our results. And from the result, it can be seen that FCFS has a rejection rate of 20% to 55%. RTCS has a rejection rate between 15 to 52%. And in case of PBOS, our proposed scheme, it's only about 10% and 35%. So in that case, you can see PBS also has a really low rejection rate. Next, we measure the number of EVs that the scheme could serve who has less SOC below 20%. From the simulation result, we have seen that PBOS select up to 10% more EVs compared to FCFS, and PBOS select up to 7% more EVs compared to RTCS. In the next slide, we're going to talk about the profit gain, because in the end of the day, we need to consider the economic benefit of the schemes. To do that, we have measured the profit gain based on this equation, and we compare our scheme with the other benchmark scheme in 3 different cases. In all of the cases, it can be seen that the proposed scheme has done much better than the other benchmark schemes. In different cases, it can be seen it is always get increasing, and in the end, we can summarize those things that the maximum profit gain over FCFS can be up to 42% and up to 24% compared to RTCS during the case 3 with 900 EVs. However, this is also increasing in all other cases. However, in the case 3, it has the maximum profit gain. So, in conclusion, we investigated a real-time EV charging scaling problem in this paper, while we considered 2 different charging modes together. And the proposed scheme PBOS has a lower rejection rate, serve more EVs with a lower SOC, and can achieve a higher profit gain compared to other 2 benchmark scheme. So as part of the future work, it can be further extended to various directions such as prediction of future load and scheduling of more EVs, and consider the flexibility nature of the EV users. And I would like to thank you to participate and listen to my talk. Thank you.